Good afternoon, everyone, and welcome back to the Physics CET session. So, yesterday we have seen the objective questions on the chapter 1, that is the rotational dynamics. So, today we will solve a few more problems on the rotational dynamics and then we will start with the module 2. Okay. So, this was the last problem that was given as a homework. So, we will solve this. So, four particles, each of mass m, are kept at the four corners of a square of length a. Okay, so refer the question. Four particles, each of mass m, are kept at the four corners of a square of length a. Okay. So four particles, they are kept at the corners of a square having the side a. The moment of inertia of the system about a line perpendicular to the plane of the square and passing through the center of the square will be. So question is, we have to find out the moment of inertia about this center. Okay. So the given axis to calculate the moment of inertia of the four particles, it is the axis passing through the center and perpendicular to this plane. Okay. So this is the point. So it is the geometrical center for this square. So to find out moment of inertia by each particle, so let us take the mass of the particle is m. So it is given mass is m. Okay. Now moment of inertia is, it is summation of mass, that is mi ri square. Okay. So it is the product of mass and square of the distance, okay, of the mass from the axis of rotation. So we have to use the general formula. So we have total four masses. So we can write this equation as m1 r1 square plus m2 r2 square, m3 r3 square plus m4 r4 square. Okay. So m1, m2, m3 and m4, all masses are equal. So we can just take the m common, and in bracket we have r1 square, r2 square, r3 square and r4 square. Okay. So what is r1, r2, r3 and r4? These are the distance of each mass from this axis of rotation. Okay. So this distance, let us take the mass m. So this is the mass and this is the axis of rotation. So this distance we can find out as, if a is the side of the square, then this distance is a upon root 2. Okay. So this distance will be same. It is a upon root 2. This is a upon root 2 and this is a upon root 2. Okay. So we can replace these values by a upon root 2. So this will be m, and r square will be, this is a upon root 2 square. So it will be a square upon 2 plus a square upon 2. This is a square upon 2. Okay. So this will be 4 times. So this is 4 upon 2 m a square. So this is equal to 2 m a square. Okay. So this is the net moment of inertia by the four masses located at the four corners of the square having the side a. Okay. So to solve such type of problem, you must know this basic formula and this geometrical condition. Okay, for this square, the diagonal is half of the diagonal is a upon root 2 if a is the side. So correct option is option C, which is 2ma square. Okay, refer this next question. So what is given here? Two bodies of masses m1 and m2 have same moment of inertia about an axis. The ratio of radius of gyration about this same axis. Okay, so we have to find out the ratio. So their moment of inertia is same for the two masses m1 and m2. So I is equal to, so formula for moment of inertia in terms of radius of gyration. So I is equal to m k square. So this is the general formula in terms of radius of gyration. Okay. So condition given is the moment of inertia is same for two masses. So I1 is equal to I2. So I1 we can write mass m1 into k1 square. This is equal to mass m2 k2 square. Okay. So question is we have to find out the relation between radius of gyration. Okay. So ratio of radius of gyration. So write this equation as k1 square upon k2 square. This is equal to m2 upon m1. Okay. And from this we get k1 upon k2. This is equal to square root m2 upon square root m1. Okay. So this is the square root m2 square root m1. Okay. So ratio k1s to k2. So this is square root m2s to m1. So correct option, it is the option B. Okay. So you should remember this basic formula for moment of inertia. It is mass into square of radius of gyration, mk square. Okay, for the next, which of the following has the smallest moment of inertia about the central axis if all have equal mass and the radius? Okay, so you should know this standard formula for mass moment of inertia. So first is the ring. We have to find out the geometry having the least moment of inertia about the central axis. So for the ring, so this is the ring, and suppose the radius is r. Okay, then it's a moment of inertia about this central axis. This is equal to m r square. Okay, then second is the disk with the same radius. So this radius is again r. So for the disk, it's a moment of inertia I is equal to m r square upon 2 about the central axis. Next geometry is a spherical shell. So for the spherical shell with radius r, it's a moment of inertia. This is 2 by 3 m r square. And for the solid sphere, for the solid sphere about the central axis, I is equal to 2 by 5 m r square. Okay. So if you refer all this formula for moment of inertia, this is mr square by 2, 2 by 3 mr square, and 2 by 5 mr square. Okay. So least moment of inertia is nothing but 2 by 5 mr square. That is for the solid sphere. Okay. So out of this geometry, ring, disc, spherical shell, and the solid sphere will have the least moment of inertia. So your answer is option D. Okay, refer the next problem. Again, it is on the moment of inertia. The moment of inertia of a solid cylinder of mass capital M and radius r about a line parallel to the axis of the cylinder and lying on the surface of the cylinder is. So, moment of inertia of the solid cylinder of mass m. So, its mass is m and this radius, this is r, about a line parallel to the axis of the cylinder. So, this is the centroidal axis. And like we have to find out moment of inertia about the parallel axis. So, parallel axis, it is on the surface of the cylinder. That means it will pass through this point which is on the surface like this. Okay. So, let us take this moment of inertia as I0 and this is the centroidal axis. So, its moment of inertia Ig. Okay. So, by using parallel axis theorem, so just I will draw the side view for that cylinder. That will be a circle. This is centroidal axis and this is the axis about which we have to find out the moment of inertia. So, this is Ig, this is I0 and this distance is the radius. So, it is r. Okay. So, parallel axis theorem is I0, this is equal to centroidal moment of inertia plus mass of the object into square of the distance between two parallel axes. So, square of the distance means it is the r square. So, Ig for the cylinder, this value is mr square by 2. So, it is similar to the disk. Okay. For the disk and the cylinder, moment of inertia is same. It is a mr square by 2 plus mr square. So, this will be 3 by 2 mr square. So, this is the moment of inertia required about the axis which is passing through the surface of the cylinder and parallel to the centroidal axis. So, correct option is option C, 3 by 2 mr square. Okay. So, you should know this formula, that is about the centroidal axis and then the parallel axis theorem. So, parallel axis theorem is I0 is equal to Ig plus mh square or mr square. Okay. Okay, refer the next problem. 5 solid spheres, each of the mass capital M and radius r, are arranged as shown in figure. So, this is the arrangement for the solid spheres. What is the moment of inertia of the system about given axis of rotation? So, this is the axis of rotation. We have to find out the moment of inertia of complete system about this axis of rotation. So, for the sphere, its moment of inertia about its own axis, that is the centroidal axis. Suppose this is the sphere and it is revolving like this. So, its moment of inertia Ig, this is equal to, it is a 2 by 5 m r square for the solid sphere. Okay. So, in this system, these three spheres, so there's namely 1, 2 and 3. Okay. So, this axis of rotation is exactly passing through their center. So, we can directly use this formula 2 by 5 mr square for sphere 1, 2 and 3. Okay. So, I will write moment of inertia just by considering these three sphere. So, this is I1 plus I2 plus I3. Okay. As the radius is same and mass is same, So this moment of inertia will be 3 times 2 by 5 m r square. Okay, so this is the just moment of inertia due to sphere 1, 2 and 3. Okay, now this sphere, which is sphere 4 and 5. Okay, so we have to find out their moment of inertia by using parallel axis theorem. Just consider one sphere. Okay, so I will draw the separate diagram. So this is the axis of rotation. This is the radius r. For this sphere, we know the centroidal moment of inertia. So we know the Ig value. We have to find out this moment of inertia. Okay. So let us take this moment of inertia as I0. So I0, this is equal to Ig plus mass into square of the distance between the two parallel axes. So it is r square. So Ig is 2 by 5 mr square plus this is mr square. So this will be 7 by 5 mr square. Okay. So this moment of inertia is just due to the sphere 4. Okay. For the sphere 5, we need to use the same formula. So its moment of inertia will be same. Okay. So total moment of inertia due to sphere 4 and 5. So just I will take this as a okay, take this I1. Okay. And this is I2. So this is I2 is equal to, it is a 2 times 7 by 5 m r square. Okay. So this moment of inertia, it is because of sphere 4 and 5. Okay. And this moment of inertia, it is due to sphere 1, 2 and 3. Okay. Now just add this two moment of inertia, I1 and I2. So net moment of inertia I, this is equal to, so this will be 6 upon 5 mr square plus 14 upon 5 mr square. Okay. So this is denominator is same. So we can just add the numerators. So 14 plus 6, 20 upon 5 m r square. Okay. So this is the final moment of inertia of the complete system about this central axis. Now select the correct option. So it is a 20 upon 5. This is directly given. So option is C. Okay. So to solve such type of problem, you should know the standard formula for the sphere about the centroidal axis. Then you should know the parallel axis theorem. Okay. Okay, now refer this problem. The moment of inertia of a thin uniform rod of mass m and length L about an axis passing through a point midway between the center and one end and perpendicular to its length. Okay. So for this solid rod, this total length, it is given as L. This is centroidal axis. So take this as a IG. Question is, we have to find out the moment of inertia at a point midway between center, that means this point, and one end. Okay, so this will be L upon 4. Okay, because this is a half distance. And again, this is center of this half. So this will be L by 4. We have to find out this moment of inertia, that is the I0. Okay, so we should know the Ig for the rod. So Ig is m L square upon 12. So this is the standard formula for the rod. ml square by 12, it is the centroidal moment of inertia. Now use the parallel axis theorem to get the value of I0. So I0 is equal to Ig plus mass of the system and square of the distance between the two parallel axes. So distance is L by 4 between two axes. So Ig is ml square by 12 plus m L square upon 16. Okay, so if you cross multiply this, then you will get the answer as a 7 upon 48 m L square. Okay, so correct option is option B. Okay, now this problem, it is on the angular momentum. So by keeping the moment of inertia of a body constant, if we double the time period, then the angular momentum of the body, option is remain constant, it becomes double, becomes half, and the quadruple, that is a 4 times. So condition given is keeping the moment of inertia of the body constant. So moment of inertia is same. If you double the time period, okay, that means it's a speed. So the basic formula for angular momentum is L is equal to I into omega. Okay. So initial momentum, let us take L1. This is equal to I. Now omega we can write as I. This is 2 pi upon t. Okay. So L1 is the initial angular momentum when we have the time period t. So we can write this as a 2 pi upon t. L2 is the new momentum. So for the new momentum, we need to double the time period. So that means we are increasing the speed. So it is I, moment of inertia is same, 2 pi upon, now time is 2t. Okay. So we have to find out the relation for angular momentum, that is L1 and L2. So just take the ratio L1 upon L2. So this is equal to, I will get cancelled. This is 2 pi upon t, and this is a 2 pi upon 2t. Okay. So L1 upon L2, so it becomes, can cancel out this. So this value is 2, L1 upon L2. That means L1 is equal to 2 times L2. So then angular momentum of the body, sorry, we need L2. So this is equal to half L1. Okay, so your correct option, it becomes half if we double the time period. Okay, so correct option is C. Okay, refer the next problem. In a certain unit, the radius of gyration of a uniform disk about its central and the transverse axis is square root 2.5. Its radius of gyration about a tangent in its plane must be, okay. So what is given in a certain unit, radius of gyration? So radius of gyration, this value k, this is given as 2.5 about central and the transverse axis. Okay. We have to find out the radius of gyration. So let us take this as a k1 and k2 about a tangent in its plane. So for the uniform disk, so this is the centroidal moment of inertia, Ig, and this is the tangent axis to the disk. So let us take this as a I0. Okay. So I0, this value is equal to Ig plus, so this distance will be radius, so mass into r square. Okay. About this centroidal axis, the standard formula for the disk is mr square by 4 plus mr square. So this is 5 by 4 mr square. Okay. Now we will equate this with the standard formula in terms of radius of gyration. So this is equal to m. I will take this k as a k2. So m k2 square. Okay. So from this, if we equate this, we can cancel out this m. So k2 is equal to square root 5 upon 2 into r. Okay. So this is the radius of gyration about this tangential axis. Now k1 value is given, which is a 2.5 about the centroidal axis. Okay. So the centroidal axis, we have I is equal to m r square upon 4. Equate this with the general formula. So m k1 square. So from this, k1 is equal to, this is r upon 2, and k1 is given as a root 2.5. So r upon 2, this is equal to root 2.5. Okay. So from this, r is equal to 2 root 2.5. So put this value in this equation. So we will get the value of k2. So k2 is equal to square root 5 upon 2 and 2 square root 2.5. Okay. So 2 will get cancelled. So in the bracket, we have square root 5 into 2.5. So this is equal to square root 12.5. Okay. So your correct option is option D. So question was, the centroidal moment of inertia, radius of gyration about the centroidal transverse axis is given as a root 2.5, and we have to find out the radius of gyration about this axis, that is axis tangent to the disk and parallel to the centroidal axis. So we should know this formula, mr square by 4, which is the centroidal moment of inertia about the transverse axis, then this parallel axis theorem, and the basic formula for moment of inertia in terms of radius of gyration. I is equal to mk square. Okay. Okay. Now this is on the kinetic energy. So a ring and the disk roll on a horizontal surface without slipping with same linear velocity. If both have same mass and total kinetic energy of the ring is 4 joule, then total kinetic energy of the disk is, okay. So when the ring is rolling, ring and disk, we can write the total kinetic energy. So for the ring, this is equal to, it's the linear kinetic energy plus rotational kinetic energy. So linear kinetic energy is 1 by 2 m v square, and rotational kinetic energy is 1 by 2 I omega square. Okay. For the ring, we know the formula for moment of inertia. It is mr square. So this is equal to 1 by 2 m v square plus 1 by 2 m r square, and omega is v upon r. So it is a v square upon r square. So from this, we will get 1 by 2 mv square plus 1 by 2 mv square. Okay, so if you add this, you will get mv square. It is the total kinetic energy of the ring. Okay. Similarly, for the disk only changes this moment of inertia. It is a mr square by 2 instead of mr square. Okay. Remaining formula is same. So just I will write the final equation for the disk. So this is equal to 3 by 4 m v square. This is the total kinetic energy for the rolling disk on the horizontal surface. And this is total kinetic energy for the rolling ring, which is mv square. So question is, kinetic energy is given for the ring, that is total kinetic energy. It is a 4 joule. So what is the total kinetic energy for the disk? So just take the ratio. Kinetic energy for the ring upon kinetic energy for the disk. This is equal to, it is a mv square upon 3 by 4 mv square. So this is equal to 4 by 3. Okay. Now for the ring, kinetic energy is 4 joule. So this is 4 joule upon disk. This is equal to 4 upon 3. Okay. So your answer will be 3 joule. Correct option is option A. Okay. So if you don't want to solve this, you can directly remember this formula, mv square for the ring, and 3 by 4 mv square. This is total kinetic energy for the rolling disk. Okay, so this is all about the chapter 1, which is the rotational dynamics. So now we will start with the chapter 2, which is the mechanical properties of the fluid. So we will see first content, and then we will start with the objective questions. So in this chapter, we have the states of matters, so solid, liquid, and gases. Then fluid and its properties. So what is fluid? What are the properties of the fluid? Then we have pressure and the Pascal law. Okay, so basically we will deal with the hydrostatic pressure. Next we have the application of Pascal law. So first is the hydraulic lift, and second is the hydraulic brake. Then pressure measurement devices. So it is a mercury barometer, U-tube manometer. So we have the formula to measure the pressure by using the mercury barometer and U-tube manometer. Next, we have the concept of surface tension and surface energy. Then angle of contact. Then shape of the meniscus. So concave and the convex meniscus. Then shape of the liquid drop on the solid surface. Next, we have the capillary action. Then the fluid in motion. Okay, so for the fluid in motion, we will see the concept of flow line, streamline, flow tube, then difference between laminar and turbulent flow. Then we have the formula for critical velocity and the Reynolds number. Okay, so basically Reynolds number, it is used to differentiate the laminar and the turbulent flow. Then we have the concept of viscosity, Stokes law, then continuity equation, for the fluid flow, Bernoulli's equation, and applications of Bernoulli's equation for venturimeter and speed of efflux. Okay, so this is the overall content of the chapter 2, mechanical properties of the fluid. So let us see this in detail. So first is states of matter. So first is solid. So in the solid, it has fixed shape and the volume when a large force is applied to it. Okay. So for the solid, the deformation is very small. So it is a negligible in case of solid. Second, liquid and gases. So for the liquid and gases, they do not have their own shape and they takes the shape of the containing vessel. Okay. So they have no rigidity. So fluid, so what is meaning of fluid? A substance that can flow, this is called as a fluid. So this is the simple definition for the fluid. So all the liquids and gases, they are called as a fluid. Okay. Also, plasma is considered as a fluid. Okay. So the substance which can flow, we call this substance as a fluid. So fluids are substances which cannot resist any shear force applied on it. So the shear modulus for the fluid is 0. So it will not offer any shear resistance to the deformation. Okay. So what are the characteristics of the ideal fluid? So ideal fluid, it is incompressible. So if we apply the pressure on that fluid, we cannot compress that fluid. So it is incompressible. Second is its flow is irrotational. Okay. So the rotational component in the fluid, all these components are 0. It is inviscid. So its viscosity is 0 for the ideal fluid. Okay. Flow is steady for the ideal fluid. Flow is steady means the flow parameters, that is a velocity, pressure at any point, do not change with respect to time. That is means flow is steady. Okay. So velocity, pressure will remain constant with respect to time. Ideal fluid do not offer any shear resistance. So shear resistance will be present if it has some viscosity. Okay. So as it is a inviscid, that is a no viscosity, it will not offer any shear resistance. Okay. So they do not have any viscosity. So shear stress, it is 0 in case of ideal fluid. Okay. So you should remember this form, this concept. Shear stress in the ideal fluid is 0. It has 0 viscosity. They can be subjected to normal compressive stress, and we call this stress as a pressure. Okay. So only stress present in the ideal fluid is compressive stress, that is a pressure. So these are the characteristics of the ideal fluids. Next is the concept of pressure. So pressure, it is given by this formula. It is a force per unit area, and its SI unit is a Newton per meter square. For the pressure, dimension is, it is L minus 1, M1 and T minus 2. And the unit that we use is a bar or the Pascal. So this is a unit conversion. 1 bar is equal to 10 to the power 5 Pascal. Okay. And 1 Pascal, this is equal to 1 Newton per meter square. Okay. Now pressure due to liquid column. So it is given by this hydrostatic equation. P is equal to rho GH. So rho is the density and its unit is kg per meter cube. G is the acceleration due to gravity. So it is a 9.81 meter per second square. And H is the height of the liquid column. So it is taken, so it is a height of liquid. This is in meter. Okay. So this pressure rho GH, it is in Newton per meter square. So how do we measure this pressure? So you can see here. So this is one container and there is a liquid up to certain height. So this height is h. Okay, and this is the bottom surface of this container. Suppose if you want to find out the pressure at this point, exactly at the bottom, so let us take this point as a. Okay, so at this point, the pressure exerted by the liquid having the height h, so it is given by equation PA, this is equal to rho GH. So just we have to measure the height above that point. Okay, the area of this container, so that means this cross-sectional area, it has no contribution in this pressure calculation. Okay, so just we have to measure the height to find out the pressure at point A. Okay, so let us see the concept of atmospheric, absolute, and the gauge pressure. So atmosphere contains the air, so it exerts the force due to its own weight, and the pressure due to force exerted by the air column. This is called as the atmospheric pressure. Okay, so simply atmospheric pressure is the pressure exerted by the air. Okay, so this pressure below the atmosphere, so it is taken as a vacuum pressure. So anything, so pressure below the atmospheric pressure, so this is taken as a vacuum pressure. Okay, so standard atmospheric pressure is, this is 1.013 bar. So if the pressure is below 1.013 bar, we will take this pressure as a vacuum pressure. Now what is absolute pressure? So absolute pressure, so this is given by this formula, P is equal to P naught plus rho GH, where P naught is the atmospheric pressure and PA is the absolute pressure. Okay, so let us take the example. So this is one container and we have the point A at the bottom. Okay, we want to find out the pressure at point A. So this height of the liquid, so this height is h. Okay, above the free surface of the liquid there is air, so this is exposed to the atmosphere. So atmosphere will exert the pressure. So this pressure is nothing but the P naught, that is the atmospheric pressure. Okay, now pressure due to this liquid height, so it is given by the formula rho GH. Okay, now the total pressure including the atmospheric pressure, so it is given by this equation P naught, which is the atmospheric pressure, plus the pressure exerted by the liquid with the height h, so it is the hydrostatic equation rho GH. Okay, so if you add these two pressures, atmosphere and the gauge pressure, so we will get the absolute pressure. So concept of absolute pressure is pressure including the atmospheric pressure, so this is called as absolute pressure. Okay, and the gauge pressure means excluding the atmospheric pressure. Okay, so from the absolute pressure, if you subtract the atmosphere, then we will get the gauge pressure. So rho GH formula, it will directly give the gauge pressure. Okay, its meaning is PA minus P naught, that is absolute pressure minus the atmospheric pressure. Okay, so difference of absolute and the atmospheric pressure, this is called as a gauge pressure. Okay, so I hope this concept is clear. Atmosphere, absolute, and the gauge pressure. So next is hydrostatic paradox. So what is hydrostatic paradox? So you can see here, we have the container of different shape, container A, B, C, and D. Okay, and we want to find out the pressure at the bottom of each container. So to find out the pressure, we just use a single equation, which is P is equal to rho GH. Okay. So if the liquid in different container is at the same level, let us take the level is H. Okay. So each container has a liquid at the same level with respect to the bottom. So it is the level is H. Okay. So everywhere pressure will remain same. So pressure is independent on the shape of the container. It just depends on the height of the liquid above that point. Okay. So from this point, just measure the height. So this height is same and therefore pressure is same. So everywhere we will have the same pressure and it is given by this equation. This is called as a hydrostatic paradox. Next, we have the Pascal law. So what is the Pascal law? Pressure applied at any point of an enclosed fluid at rest is transmitted to every point of the fluid and on wall of the container. Okay, so you can see this diagram for the Pascal law. So if you press this ball, then it will create the pressure and this pressure will get equally transmitted to all the directions. Okay. So based on the Pascal law, we have two applications. One is the hydraulic lift and second is the hydraulic brake. Okay. So in the hydraulic lift, by using very small amount of force, we can lift the heavy weight. Okay. So this is the simple arrangement for the hydraulic lift. You can see here, this is cylinder and piston arrangement. Okay. So for this cylinder and piston, this cross section area, this is A1. Okay. And the force applied on this piston is F1. So pressure created at this cylinder, P is equal to force upon area. So it is F1 upon A1. Okay. Now pressure which is created at this cylinder will get transmitted to the other side. Okay, so this pressure will remain same. Now here the force created, this is the F2 and the cross section for this cylinder is A2. So here pressure is F2 upon A2, but pressure is same. So which is a P1, P2. So P1 is equal to P2. So F1 upon A1, this is equal to F2 upon A2. Okay, so if we apply very small amount of force, we can calculate the load lifted at other side of the hydraulic lift. So we can calculate the F2 value. So this will be F1 into A2 upon A1. And similarly, we have the other application, which is the hydraulic brake. Next is the pressure measurement. So first instrument, it is the mercury barometer. So mercury barometer, it is used to measure the atmospheric pressure. Okay. So mercury barometer, it consists one inverted glass tube, which is immersed in the mercury. Okay. So by using the rise of the mercury in this tube, that is the height of the mercury, we can find out the atmospheric pressure. So we have the equation, pressure at point B. So at this point, this is equal to pressure at point A plus rho GH. Okay. So in this tube, above the point A, so this is a vacuum. Okay. So for the vacuum, we have the pressure 0 at point A. So pressure at point B is nothing but the rho GH. Okay. And this rho GH, that is the pressure at point B. So in the liquid at the same level at different point, pressure will remain same. Okay, so C and B point, they're at the same level. So pressure at point B, this is equal to pressure at point C. Okay, and at the point C, it is exposed to the atmosphere. So pressure at point C is nothing but the atmospheric pressure, that is a P naught. And therefore, PB is nothing but P naught, that is the atmospheric pressure. So this level of mercury in this tube, it will directly give the reading of the atmospheric pressure, and its formula is rho gh. So this is how you can use the mercury barometer to measure the atmospheric pressure. Now the atmospheric pressure in terms of height of mercury is P atmosphere is equal to 76 centimeter of Hg, that is the mercury, or it is 760 mm of the mercury. And if the pressure is below the atmospheric pressure, so we call this pressure as a vacuum pressure, and it is measured in the unit torr. So this is the unit used to measure the vacuum pressure. And the relation between torr and mm of Hg is 1 torr is equal to 1 mm of Hg. So this is the vacuum. Now second instrument to measure the pressure is U-tube manometer. So this is generally used to measure the gauge pressure. So suppose this is the pipe, it carries some fluid, and we want to measure the pressure in this pipe. So let us take this point as a point A. Okay, we want to find out what is the pressure at point A. So in order to measure this pressure, we have connected one U glass tube. Okay, and this glass tube, it contains the liquid, which is the mercury. So it is the heavier liquid or the heavier fluid. So this pressure get transmitted in the tube, and it will push the liquid on other side. Okay, so you can see the rise of level of the mercury. So this rise of level, let us take this as a H. Okay, so pressure at this point, at this level, it is equal to the pressure of the liquid in the pipe. So it will be PA, and this is equal to, so pressure exerted by the liquid having the height H. So this is equal to rho gh, and plus we have to add the atmospheric pressure. So this is the P naught. Okay, so PA is the absolute pressure at the point A in the pipe. This is equal to rho gh, which is the gauge pressure, plus P naught. And if you just find out the gauge pressure, then it is equal to rho gh. Okay, so by using the height of the mercury in the U-tube, we can find out the gauge pressure of the fluid in the pipe. By using U-tube manometer, we can measure the vacuum pressure also. Okay, suppose this pipe has a vacuum pressure. Okay, let us take this point as a, and this pipe has vacuum. Okay, and we have the manometric fluid as a mercury only. So because of the vacuum, it will suck the mercury in the left side of this U-tube. Okay, therefore on the right side the level of mercury will be lowered compared to the left side. So you will get the difference of height like this. Okay, so level of mercury in the left side will be greater than the level of mercury in the right side. So this difference of the level, this is H. So here, as a PA is the vacuum pressure, so this line is the equilibrium line. Okay, let us take this line as a XX. So pressure on left side at this point, it must be equal to pressure on the right side at the same level. So at this point, total pressure is nothing but the PA plus. So at this point, total pressure is nothing but the same pressure in the pipe, plus we have to add the pressure due to the mercury height. Okay, so this height is nothing but H. So this pressure is rho GH. This is on left side of the U-tube. In the right side, at this point, pressure is the only atmospheric pressure. So this is the P naught. Okay, so PA, this is equal to P naught minus rho GH. So this is the absolute pressure, that is absolute vacuum pressure. Okay, and just if you want to find out the gauge pressure, you can neglect this P naught. So PA, this is equal to minus rho GH. So negative pressure is nothing but the vacuum pressure. Okay, so same U-tube you can use to find out the pressure above the atmosphere and pressure below the atmosphere. Okay, now next concept is the surface tension. So surface tension, it is defined as the tangential force acting per unit length on both the side of an imaginary line drawn on the free surface of the liquid. Okay, so if you consider this is the free surface of the liquid, and this liquid, it is under tension. Okay, that is this layer. And if you consider one imaginary line, then this is the force acting on this imaginary line. So this is the force due to surface tension. Okay, so surface tension we can find out by using this equation. T is equal to F upon L. Okay, and its unit is Newton per meter, and its dimension is L0 m1 T minus 2. So because of surface tension, the insect floats on the water. So this is the example of the surface tension. Okay, if you drop the needle, it will float on the surface of the water. So this is again due to the surface tension. So reason of the surface tension is, first is the intermolecular force. Okay, so in the intermolecular forces, we have cohesive force and the adhesive force. So what is cohesive force? It is attraction between the molecules of the same substances, that is called as a cohesive. So this force is strong in the solid. So cohesive forces is strong in the solid and weak in liquid and gases. Due to this, solids have the definite shape. Okay, so if the cohesive force is large, then it will try to attract the molecule. Okay, and therefore solids have the definite shape. Liquid droplets coalesce into one drop due to the cohesive force. So if you have the number of liquid droplet, okay, so because of cohesive force, they will come together and they will form a single drop. Next is the adhesive force. So force of attraction between the different molecules or the molecules of different substance, that is called as a adhesive force. So because of adhesive force, water droplets sticks to the glass surface. Okay, so this is example of the adhesive force. Now the surface tension. So this is one relation for mercury, water, and the glycerin. Surface tension in mercury is the highest, then water, and then glycerin. Okay, so numerically, surface tension for mercury is 0.43. This is a Newton per meter. For water, it is 0.072, and for glycerin, it is 0.063. So you should know this relation. Mercury has highest surface tension, after that water, and then glycerin. Now next is the surface energy. So surface energy means work done on stretching the surface film by amount dA is stored as a potential energy, and this potential energy is nothing but the surface energy. Okay, so let us take this soap film, which is formed due to this thin wire having the rectangular shape. Okay, suppose at this line, if you apply some force and if you increase the surface area of the film, so this is the increased surface area. When we apply the force F, then the work done or the potential energy stored, this is equal to T into increased area. So this increased area is nothing but the D. Okay. So by using this formula, we can find out the surface energy. Surface tension from this formula, surface tension, this is equal to W upon dA. So surface tension is also called as surface energy per unit area. Okay, so this is surface energy per unit area. Now next point is the angle of contact. So first is the concave meniscus. So for the concave meniscus, the angle of contact, it is the acute angle. Okay, so we observe such type of acute angle in the concave meniscus, and example is water and glass. So liquid which partially wets the solid surface, for this we observe the acute angle of contact, and example is water and glass. Okay, second is the convex meniscus. So it is the obtuse angle, that means theta here is greater than 90 degree. So glass and mercury, this is the example for the convex meniscus and the obtuse angle. So here liquid does not wet the solid surface. So convex meniscus, it is formed because of the high cohesive forces. Okay, so here the cohesive forces greater than the adhesive force. And the example is again glass and mercury. So for the obtuse angle. So this is the relation, how the acute angle, obtuse angles are formed. So you can see this vector diagram. So here we have AP, this is the adhesive force, AC is the cohesive force, R is the resultant of these two forces, okay, and T is the tangent which is drawn to the meniscus, okay. So for the acute angle of contact, AP bar, that is a net adhesive force, is greater than AC upon root 2. Okay, so AC is the cohesive force. For obtuse angle of contact, the AP bar, that is the adhesive force, is less than AC upon root 2. So in this case, the angle theta is greater than 90 degree.
So here theta is less than 90 degree when AP is greater than AC upon root 2. So you should know this relation. And if you consider the one hypothetical condition where the angle of contact is exactly 90 degree, then AP bar, that means adhesive force, it is equal to AC upon root 2. So here you can see exact 90 degree angle of contact. And for the liquid that completely wets the solid surface, theta is equal to 0. Sorry, this is not 90 degree. This is theta, this is equal to 0. For the liquid which completely wets the solid surface. Okay, so we can take the example of pure water without any impurity. For the pure water, angle of contact is nearly 0. That means water completely wets the solid surface. Okay, so in this case, when theta is equal to 0, AC bar, that is a net cohesive force, so this is 0. And AP bar is equal to the AR bar. So net, that is the resultant, is nothing but the net adhesive force. So here adhesive force is very greater than the cohesive force. Okay, now we will see the shape of liquid droplet on the solid surface. Okay, so shape of droplet depends on the surface tension and the angle of contact. So if suppose T1 is surface tension at the liquid and solid interface, T2 is the surface tension at air and solid interface, T3 is the surface tension at liquid and the air interface. Okay, then all these forces are tangential at the surface in contact. So you can see here, this is T3, T1 and T2. Okay, so for the equilibrium of the drop, T2 is equal to T1 plus T3 cos theta, or cos theta is equal to T2 minus T1 upon T3. Okay, so first is acute angle. So depending on the angle of contact, it will decide the shape of the droplet. So for the acute angle, T2 is greater than T1 and T2 minus T1 is less than T3. So in this case, cos theta is positive and theta, it will become acute angle. So example is water on the glass. For the obtuse angle, that is for the mercury, T2 is less than T1 and T1 minus T2 is less than T3. Okay, so in this formula of cos theta, which is T2 minus T1 upon T3, so here cos theta becomes negative. Okay, and as the cos theta is negative, that means theta is obtuse, which is a greater than 90 degree. So mercury on the glass, this is example for the obtuse angle of the droplet. And if T2 minus T1 is greater than T3, then cos theta is greater than 1, which is an impossible condition. Okay, for such cases, drop will not be formed and the liquid spreads over the surface. Okay, so here we should know this formula, which is for cos theta, T2 minus T1 upon T3. Now, what are the factors affecting the angle of contact? Okay, so first is nature of liquid and the solid in contact. Second, impurities present in the liquid that change the angle of contact. And third is the temperature. So any increase of temperature of the liquid, it will decrease its angle of contact. So if temperature increases, angle of contact it will decrease. Okay, so factor affecting is nature of solid and liquid, then impurities present, and the temperature. Now, factor affecting the surface tension. So, first is impurity. Surface tension, that is a T. So, for the impurity, when soluble substance like sodium chloride is dissolved in the water, surface tension increases. Okay, that means when we add the soluble impurity in the water, then its surface tension, it will increase. Second, when substances like phenol or the detergent is mixed with the water, surface tension decreases. Okay, so when we add the detergent in the water, its surface tension, it will decrease, and because of this, water makes good contact with the cloth. Okay, so when the surface tension of water is decreased, it will make good contact, and so water makes good contact with the fabric and it removes the turf stains. Okay. Third is when insoluble impurities added into the water or mercury, surface tension decreases. Okay, so when we add the insoluble impurities, then surface tension will decrease. Due to this, cohesive force of the liquid decreases. Okay, that means when we add the impurity, cohesive forces will decrease, and that will decrease the surface tension. So it affects the angle of contact and the shape of the drop. So if mercury gathers dust, it cannot form the perfect spherical droplet. Okay, because the cohesive forces decreases when we add the dust in the mercury. So these are the factors that affects the surface tension. And next is the temperature. So in most of the liquid, as temperature increases, surface tension decreases. So in case of molten cadmium, so these are two exceptional cases, molten cadmium and the molten copper. Surface tension increases with increase in the temperature. Okay, and for rest of the liquid, if we increase the temperature, then surface tension decreases. Now pressure inside the droplet and the bubble. So for the drop, so when liquid drop is to be formed, the pressure inside it is given by Pi minus P0. This is equal to 2T upon R. Okay, so this equation, this is called as a Laplace law of spherical membrane. And when soap bubble is formed, so this is Pi minus P0, this is equal to 4T upon R. So you should remember these two formula. There can be a question on this formula. For the droplet, it is 2T upon R, and for the soap bubble, it is a 4T upon R. Because for the soap bubble, it has two surfaces, inside and outside surface. Okay, and for the drop, it has only one surface. Okay, so for capillary action, fluid motion, we will discuss in the next lecture. So now we will solve some objective questions. Okay, so first concept is pressure and the Pascal law. So question here is, the pressure at the bottom of the liquid tank is not proportional to, first is acceleration due to gravity, density of the liquid, height of the liquid and area of the liquid surface. Okay, so suppose we have the tank, and this tank is filled with the water or any other liquid. Okay, at the bottom, height of the liquid above the point, it is H. So pressure at this point P, it is given by the hydrostatic equation rho gh. Okay, so this pressure, it depends only on density, acceleration due to gravity, and the height. Okay, it does not depend on area of the liquid surface. Okay, that means on this area pressure is not dependent. So your option is option D. Pressure at the bottom of the liquid is not proportional to, that is the area. Okay, in the hydraulic press, small f and the capital F are the forces acting on the small piston and the large piston, having the diameter small d and the capital D. Then F upon F is, so we have to find out this ratio. So for the hydraulic press, so it is similar to the hydraulic lift. So this is having the diameter D1, or we can take small diameter, and this is the large diameter, so it is a capital D. Okay, pressure here, it is a small f, and this pressure is capital F. Okay, so pressure in this hydraulic press, it will remain same as per the Pascal law. Okay, so pressure gets equally transmitted in all direction. So pressure is same, so F upon A, or this small a, this is equal to F upon A. Okay, so F upon capital F, this is equal to small a upon capital A. So this is A means pi by 4 d square upon pi by 4 capital D square. Okay, so this will get cancelled. So this ratio is nothing but d square upon capital D square. So your correct option is option D. Sorry, option C. Refer the next problem. The ratio of area of cross section of two pistons in a hydraulic machine is 1:15. Okay, so ratio of cross sectional area is given. Find the force that should be applied on the narrow piston to overcome a force of 120 Newton on the bigger piston. Okay, so this is one hydraulic machine. This is the smaller piston, and this is the bigger piston. Okay, this is having the cross section. Let us take A1, and this is A2. Here we have the force F1, and this is F2. So pressure is same. So F1 upon A1, this is equal to F2 upon A2. Okay. So what is given? The ratio of cross-sectional area is given. That means A1 upon A2 is given. So A1 by A2, this is equal to 1 upon 15. Okay. So this A1 by A2, from this formula we can write. So this is F1 upon F2. Okay. So F1 narrow piston, force applied, find the force that should be applied on the narrow piston. That means we have to find out the F1 value, and F2 is given 120. So F1 upon 120, this is equal to 1 upon 50. Okay, so F1 is equal to 120 upon 15. So this is 8. So your correct answer is option D, 8 Newton. Okay. So for such type of problem, you should remember this formula, which is the Pascal law, F1 upon A1 is equal to F2 upon A2. Okay, next point is fluid motion. So fluid motion, the first problem is, in a laminar flow, the velocity of flow at any point in the liquid first is does not vary with time, may vary in the magnitude but not in the direction, may vary in direction but not in the magnitude, and may vary both in magnitude and direction. Okay, in laminar flow, velocity of the flow at any point in the liquid so it does not vary with the time. Okay, refer the second problem. Which of the following is not the property of the laminar flow? So flow may be along the curve path. So laminar flow means what? So fluid particle in different layers, they move exactly parallel like this. Okay, so this is called as a laminar or the streamline flow. Particles do not mix into each other. Okay, so they remain in a single layer. So for this laminar flow, flow may be along curve path. So laminar flow, it can take place in a curve path like this. Okay, so this is possible. Velocity of the flow is independent of the time. Velocity of flow may be different at different point, and liquid molecules may cross from one layer into other layer. So this is not the property for laminar flow. Laminar flow means what? Fluid particles should not cross from one layer to other layer. Flow may be along curve path. This is possible condition. Velocity of flow is independent of the time. This is also possible. Velocity of flow may be different at different point. This is also possible. Okay. So correct option is option D. It is not the property. Okay, so today we will stop here. The viscosity and other concept we will discuss in the next lecture.